say that fantastic because I want to
All right, thank you for coming to the morning session of day 2. I'm delighted to introduce our first speaker, Sasha Rakhlin of UPenn. He's now also spending time at MIT. And he'll be telling us about algorithms for learning on graphs.
Thanks for the invitation. Pleasure to be here. The mic is on, right? Okay. Okay, so I will talk about work with Karthik Sridharan. We've been working for a while on problems of online prediction, online learning. Today what I will discuss is just a very easy example, of just a snippet of the results. If you're interested in all the gory details, I can refer to the papers. So on purpose, I want to make this very simple, so the simplicity is my goal here. All right, so if you think about the usual prediction paradigm that we have in machine learning, it's always to collect some data, then estimate some model, and then make prediction based on the estimate of the model. And so for the problems that we're interested in this talk, this middle part, the estimation of a model, somehow is a computationally hard problem, computationally hard objective. And so the question is whether one can directly go to prediction, avoiding the model estimation part. If you would like to have a takeaway from this talk is that, yes, in the problems that we'll consider, it's possible to predict even if estimation is NP hard. So somehow by avoiding estimating the model, going directly for prediction, we can still have a computationally efficient algorithm. And this idea is perhaps not new. If you think about the beginnings of machine learning in the 60s, people realized that if you want to distinguish male versus female faces, let's say, then you don't have to estimate the model for the distribution of the male faces and the model of the distribution for the female faces, and you go directly for the boundary between them, right? If prediction is your goal, right? So go for the simpler problem rather than solving the more difficult problem along the way. Okay, so what I would like you to keep in mind is kind of this problem. There's a fixed social network, and one by one we have to make predictions about labels, let's say binary labels or multi-class labels for each person. So think of this person as opening a Facebook page. You need to design a system that will display ads. And so you need to predict, you need to classify this person as type 1, type 2, or out of multiple types. And then you learn the outcome, whether the person clicked or didn't click on the ad. So let's just say it's a full information setting, so you actually learn the true label. And you go on and so forth. So you move within the network. And the prediction should be made based on the side information at the node. So you have some information about the covariates for the person, male, female, gender, age, and so forth, based on graph connectivity. Okay, so that should be taken into account. And the information that you've gathered so far. Okay. So this is the problem, kind of a running problem, and the question is, how should we model this problem? Let's say we want to solve the problem. How should we approach this problem? Well, we can, if we're Bayesian, maybe if we're statisticians, we would like to posit a probabilistic model. For instance, community detection is one example. If you think that there will be two communities, one is, prefers to buy this type of product, this prefers to buy another type of product. Maybe that's a community detection model. Perhaps we can phrase it as a huge dynamic program and somehow figure out the optimal way to predict at every time step and so forth. So what are the computationally efficient methods? One can just try to run batch algorithms at every time step, such as Laplacian regularization, and hope for the best. Okay. And again, the question here is estimation versus prediction. Do we need to actually estimate some model? Do we have to posit a model and estimate it? Or can we just bypass estimation? Another word that I'll be using is proper versus improper learning. So proper meaning you first estimate a model and then give out the prediction according to the model. Improper avoids this step. And what we will do is we will model solutions. Just like in the example of faces, male versus female, the solution is a hyperplane. We'll model the solutions rather than the process that generates the data. And what we will have is a knob that trades off computation and the statistical performance. So let's be a bit more precise. If you're not concerned with computation, then in the online learning community, what we like to prove is that our average prediction error is upper bounded by the oracle error. That's the comparator. That's the best you could have done in hindsight if you had all the data. And plus a little O of one remainder, and you hope that this goes to 0 at a certain rate. So that's if you don't care about computation. Now suppose that oracle error, you can't compute that. So this is an NP-hard problem. Even in hindsight, with all the data, you can't compute it. But you can say, suppose that we have an alpha approximation for the oracle loss, for that offline problem. Then you would like to have alpha times, well, you might hope to get alpha times oracle error. And something like this has been done, for instance, in the paper of Kalai, Kakadi, and Liget. What we will do is, by avoiding model estimation, we're going to get oracle error with a constant 1. So it's 1 times opt, plus, and alpha will only enter in this lower order remainder term. Okay, so and this at this point it seems very strange. Why would this be possible to do? But I will describe it in such a simple terms that you will see that it's actually kind of obvious why this should be the case. Okay. Why is this result not too interesting in the sense that well, it could very quickly be vacuous. So suppose that the oracle error in terms of prediction is 5% prediction error, right? And alpha, typically we have a multiplicative approximation of, I don't know, square root of log n or some factor 2. Then quickly this becomes, you're comparing yourself to some very high number. So the result quickly becomes vacuous. Okay, so I will present the results through the lens of this very classical result of Tom Kover in 1965. I guess this paper is almost unknown. The result is very simple. Yes?
So you'll be able to do everything that Adam and Katrina and Sham did?
Slightly different framework. We're going to talk about prediction. So it's going to be the indicator loss.
You cannot handle like online problems in general.
It's not the general online problem, right? That's correct. It's going to be a prediction problem. That's right. Okay, so I will describe everything through the lens of this result. Let's describe the most basic sequence prediction problem you can have. There is a sequence of bits, y1 through yn, plus minus 1. And we would like to make sequential predictions, y hat 1 up to y hat n, where the predictions are causal. So the y hat t only depends on the bits that have been observed. So once you make a prediction, suppose that you observe the outcome right away, make a prediction y hat 1, observe the y1, y hat 2, observe y2, and so forth. So the goal is to have a small number of prediction errors. Okay, that's the goal. So can we predict this sequence? So fix any algorithm, randomized or non-randomized. Any algorithm will be worse on some sequences and better on some other sequences. If it is better on some sequences, it has to be at the expense of being worse on some other sequences. Okay, maybe it's not too obvious, but if you think about averaging this quantity over 2 to the n sequences, and then carefully switching the expectations, you see that in expectation over the hypercube, on average over 2 to the n sequences, this quantity has to be 1/2. So there is no free lunch, right? So if the algorithm is better on some sequences, it has to be at the expense of being worse on some other sequences. But the interesting question which was asked by Tom Kover is the converse. If I tell you which sequences I care about, can you construct an algorithm, right? So that's the interesting direction. So any algorithm induces a profile on the hypercube. That's the expected number of mistakes on every corner of the hypercube, on every vertex of the hypercube. And the opposite is, if I tell you this function on the hypercube, is there an algorithm that achieves that function, right? So let's make it a little bit more precise. We'll say that the function phi is achievable if there exists a randomized strategy. It has to be randomized, so we have to work with randomized strategies, such that for any sequence y1 through yn, that's my notation for a sequence y1 through yn, the expected, under the randomization of the algorithm, average number of mistakes is upper bounded by the function of that sequence. Okay? So that's what it means for a function phi to be achievable. Now let's only consider phi such that when you flip one bit, it's a function on the hypercube, so when you compare the function values along the edge, the difference is no more than 1 over n. If you consider these functions, then the result of Kover says that phi is achievable, so there exists an algorithm, if and only if, on average over the hypercube, these are random or random variables, plus or minus 1 uniformly and independently, is at least 1/2. Okay, so whenever you take a function, you check that its expectation on a uniform distribution over the hypercube is more than 1/2. There exists an algorithm that will achieve that function. Okay. And so anyone here can prove it. The proof is about 1 page. You just sit down and write it as a kind of work backwards. Kover didn't even actually prove it, but he just stated that it's obvious. But it actually requires a little bit of a proof. Let me just make a note that this is the simplest example of an interesting phenomenon that I think we only formalized a year ago. That existence of prediction algorithms is equivalent to probabilistic inequalities. So that's an interesting phenomenon. So just to give examples, if we think of experts, the experts algorithm, the exponential weights algorithm, I think it's kind of a folk result that it's equivalent to a union bound, right? So the expected maximum of n sub-Gaussian random variables is square root of log n, and that is exactly the square root of log n that appears in the exponential weights. And if you go through the proof, at some point you use exactly the kind of the union bound for sub-Gaussian random variables. But this equivalence is actually quite a bit more general. So there's a paper that we posted. It's called On Equivalence of Probabilistic Inequalities and Deterministic Regret Statements. All of these results are deterministic per sequence, and these results are probabilistic. And so there are some examples there where, for instance, gradient descent can be shown to be equivalent to inequality tail bounds for ratios of a norm of a sum of random variables divided by its variation, square root of the sum of the increments. Yes?
Is there an implicit statement about efficiency of the algorithm, or is it simply that there? I mean, it seems to me that it could involve something that was computationally intractable.
Yeah, there is nothing about computational efficiency here. There is nothing, right? That's a good question, right? Just existence of algorithms. Okay, so this is just to maybe to pique your interest, but yes.
Can you give an example of phi that is not achievable?
Yeah. Well, if take any function whose expected
Just an example.
less than 1/2. What's that?
An example of one function.
Suppose you're trying to predict. Okay. Take the minimum of the proportion of ones in the sequence and the proportion of minus ones. Okay.
Okay.
If you check the expected value of that function, it's actually less than 1/2. And I'll give plenty of examples. You'll see. Okay. So somehow this magic happens for this particular setting. binary labels, indicator loss, no covariance, and what we've been kind of working on is to characterize what is possible within the community. It's not just us. Under which conditions can we get algorithms or prove their existence? Again, so it led us to some interesting martingale extensions of empirical process theory that certify existence of algorithms. Okay, so here's a canonical construction. We need to pick a function whose expected value is more than 1/2. The canonical construction is to take a subset of the hypercube. So let f be a subset of the hypercube. And let phi be a normalized Hamming distance to this set. Okay, so that's a canonical construction. This is the one that has been studied within the online community for the last 20 years. Okay. Let me say this again. Why are we doing this? So the result of Kover says that any algorithm is basically there is no free lunch. So any algorithm will have half average error on all the sequences. But we want to turn the tables and we want to say, okay, we're actually going to use this function phi to model the problem. In other words, we don't care about all the sequences, right? We only care about some sequences. We could model this probabilistically, which would lead to a completely different set of results. Or we could model it through this function phi as the set of possible solutions. And yes, this function phi, we're going to make it small on those sequences that we care about. And it will be at the expense of being large on some other sequences. But we don't care about those sequences. We're not going to see them, right? That's kind of the rough idea. Yes?
So is this related to the idea of typical sequences in information?
Yeah. So many people ask this. So I don't know how to formally relate this because these results are completely deterministic. But I think you can think of that as maybe the set that you expect to see. But there is no probabilistic generative model for these sequences. Okay, so this is canonical construction. And if you know online learning, you've seen this before. It's just rephrased slightly differently. Okay, so if we take this canonical construction, we need to ensure that the expected value of phi is at least 1/2. But if you look at this function phi as a Hamming distance, you see that its expected value is not 1/2. It's less than 1/2, right? If the set f is non-empty, then the expected Hamming distance to the set is less than 1/2, right?
Unless it's a singleton.
Unless it's a singleton, right? But you see that if the set f is not crazy, then it's just slightly smaller than 1/2. So you just need to correct it, right? So what is the correction? The correction is some constant, right? It only depends on the set f. And it's easy to see that the smallest value of the constant that makes expected value of phi more than 1/2 is precisely these Rademacher averages. These are called Rademacher averages of the set f as a subset of the hypercube. It's a correlation of elements in f and random signs. Oh, sorry. Yes. Sorry. This should be Cn. I changed one and didn't change the other. Yeah. Yes. Apologies. So this should be Cn. So what is Cn is the average width of f. If you know the Gaussian width, this is a very related concept. So somehow it's the average width of the set f when you look on average over the directions towards the vertices of the hypercube. Okay, again, this is not a new result. You can find it, for instance, in Nicola and Gabor's paper in Annals of Statistics in 1999, for instance. It's just phrased slightly differently. Okay, so these are Rademacher averages from statistical learning. And just as a side, there are no covariates here. There is no graph. But if covariates are present, then what you would get instead of this Cn, you would get sequential Rademacher averages where, again, you're correlating random signs with values of the functions on the data. But now these data, it's a predictable process with respect to the dyadic filtration generated by the same epsilons. So this creates a supremum of a martingale and a supremum of a bunch of martingales indexed by elements of f and leads to this kind of extension of the empirical process theory. Okay, the result of Kover is actually algorithmic. So if you go through the proof, if you actually write down the proof, you'll see that it's algorithmic. And this is the optimal algorithm. And what does it look like? You take the function phi. All right, so we have to have a randomized strategy. A randomized strategy for predicting 1 or -1 is just the mean of the distribution on +1, -1. And that's a number between -1 and 1, right? So all we have to do to specify an algorithm is to provide a value between -1 and 1 given the sequence so far. And that's what we're going to do. That value is a difference of the phi function where the first t-1 coordinates are fixed, then you put a -1, and then you fill the rest with coin flips, okay? Random +-1s. And then from that you subtract the same thing with a +1. So think of this as a difference of the potential. If the potential here is the same as the potential here, in other words, it doesn't matter whether you put a -1 or a +1, then this value q hat is 0, and that's the unbiased. So I don't care whether I should be playing -1 or +1. It's an uninformed choice. And then you have to scale by n just to get to the right scale. And this is where you see the condition of that the function phi shouldn't change along the edge by more than 1/n. That's where this comes in. And there is an expectation over the coin flips into the future. And this just comes out from the minimax analysis. It doesn't, and this is a well-known result, this comes out from the minimax analysis. It does not mean that we're assuming future is, IID random. We're not placing any assumptions about the actual sequence that we will see, but this is the solution that comes out of the minimax analysis. Okay. So what do we need to do? Well, we need to evaluate the value of phi function twice. And you see the bilinearity of expectation. You can just draw these epsilons and then drop the expectation. This is a doubly randomized strategy that works correctly in expectation. And all we need to do is to compute the Hamming distance or compute the value of the phi function at this point and at this point. Of course, that constant that shifts the phi function doesn't matter, right? Because it cancels in the difference. And the only thing you need to do is to compute the Hamming distance from this point and from this point to this set, right? That's what you need to do. In fact, you need to just see how much closer on average this one is to the set. And these predictions are improper, right? We're not finding a model, we're not estimating some model and then outputting predictions according to that model. We just need to do something, right? Okay, here's an example. So let's come back to Yishai's question. Suppose that you want to predict a sequence and you think that it's going to be imbalanced. Okay, so there will be more 1s than -1s or more -1s than 1s, suppose. Then what you can do is you can take the set F to be 2 points. One is the all 1s and one is all -1s. And then this Hamming distance, it's easy to see, it just becomes the minimum between the average of 1s and the average of -1s. Right? The frequency of -1, frequency of +1s. And then you need to correct it by basically square root of log 2 or some multiple of that over square root of n. Now what is the interpretation? Well, if you use this phi function in the algorithm, it means that if the sequence is imbalanced, so let's say it has 40% 1s and 60% -1s, then you will make only about 40% errors. Right? If the sequence happens to be 20%, 80%, you will only make roughly 20% errors. And this is not a trivial result, right? I mean, if you think about trying to design such a method, there is no stochasticity in the sequence. Of course, if you knew it's Bernoulli, you just estimate the bias and then proceed with the majority. But you get essentially the same result without an assumption about the generative process of the sequence. Okay, and there is a nice paper. I guess it's one of the last papers that David Blackwell wrote in 1995 that basically discusses this interesting duality between assuming the generative process for the sequence and then having a deterministic algorithm, or having a randomized algorithm that works for any sequence, right? And the results that you get are the same. Okay, so yeah, so I should say that here it's easy to see that any algorithm that you come up with has to be randomized, because for any deterministic algorithm there exists a sequence that will exactly does opposite of what you are going to predict, so there is no way to achieve this result with a deterministic method. Okay, so what are some graph-based functions here? So now we want to bring the graph into the picture. Let's start with this kind of community detection style picture. This is the data set that was beaten to death by the community detection community. This is a political blog data set, has lots of Democratic blogs that link to each other, and then Republican blogs that link to each other. This data set is at least 12 years old, maybe more. And there are fewer edges in between. So what do we expect? Well, if we think that we want to model homogeneity of a labeling with respect to a graph, then it's natural to define the set F as those labelings, so these are vertices of the hypercube, such that the value of the Laplacian is less than some value kappa. Okay, that's a modeling choice. So here's the Laplacian. I'm sure all of you know. It's just the diagonal minus the adjacency. And you can have a weighted Laplacian as well if these are trust-distrust networks with possibly plus, minus weights indicating a repulsion and plus weights attraction. And more generally, this is an example of what's called the CSP in the computer science community, where you can define the set F to be those labelings over the nodes, such that some kind of some of the constraints is not too violated, not too much violated. Okay. This is a more general formulation. So in this example, n, the length of the prediction problem, is the number of nodes. We're assuming that you will just go through all the nodes and make prediction one by one. Okay, so these cut-based constraints very quickly become NP-hard, and it's easy to see it. So for instance, if you take weighted undirected graph and define the weighted Laplacian this way, then evaluating the Hamming distance is as hard as computing the minimum of this quadratic form. And then that becomes a min uncut if you take weights to be -1s. And so this, essentially evaluating the Hamming distance is an NP-hard problem. Okay, so that's what I promised in the beginning. We have a natural formulation where you would like to predict as well as the best labeling that is smooth with respect to the graph in a certain sense, but the problem is NP-hard. And the first idea is to just approximate this Hamming distance. And there are multiplicative approximation algorithms, but I do not know how to use such an approximation result within the prediction setup, right? So you need to compare the Hamming distance from 2 points to the set, and it's not clear what having an approximation buys you. Maybe there is a way to do it, but we don't know. I will show you a way that gets around that problem. So it's still possible to get the mistake bound. And the idea is very simple. So suppose that this set F is difficult to compute the Hamming distance to, and you take a larger set, F prime, so that you have a relaxation. And then it's easy to see that if you define the function phi prime now with respect to the distance to this larger set, then, of course, the Hamming distance now goes down because it's a larger set. But this Rademacher averages, the width of the set, becomes larger. And so, of course, trivially, it's upper bounded by the Hamming distance to the original set, and this number became large. How much larger? Well, it's just the average of the expansion, right? How much did we lose in making the set F larger? And so you already see the kind of why the approximation only enters in this lower order term. It doesn't enter. You still have 1 times the opt, right? This is the prediction error compared to the 1 times opt, and this factor becomes worse. So what's interesting is to see how much this factor becomes worse. And so do we have an example where we can control kind of how much worse this factor is? In particular, we would like to have a trade-off between accuracy and computation. So this idea that you take a larger set F and you get better computation, but perhaps worse guarantee on the number of mistakes. Another interesting observation is that we only need the value of the relaxed problem. We don't need the integral solution. So we don't need to round the solution to be integral, which is, of course, a big part of the work in the computer science community. OK, so let me summarize. For the particular example of CSPs, if we have an alpha approximation algorithm for the CSP, then we will have the number of mistakes that our method makes compared to this combinatorial objective. And this is the larger little of 1 factor. And how much larger? We will see now that it's the width of a set where the number of constraints is enlarged by alpha. Alpha being the multiplicative approximation, the integrality gap.
So
yes?
I got a bit lost. So in that CSP problem, you are trying to label +1, -1, the whole hypercube or F. So what's the connection to the Hamming distance problem?
Right. So basically, the canonical way to define a function phi is to take a subset of the hypercube. And now this subset of the hypercube is going to be given by this type of CSP formulation, where we only look at those labelings that do not violate the constraints by more than a kappa. And now we would like to see how relaxing this set affects the computation and the precision. Any other questions?
The vertices are coming online.
So the vertices are all the labelings of all the n elements. And what you observe is 1 more coordinate at a time. Coordinate number. Okay, so this is how we bound the width of the larger set versus the width of the original set. So I don't know if I should go into this. Basically, we lift the problem into a semi-definite relaxation or sum of squares, whatever Lasserre hierarchy, whatever you want. So we write as SDP, but this can be this kind of analysis works for a general way to solve the combinatorial problem. So you go to this is the original problem. You would like to maximize beta. Yeah, I should say that the Hamming distance, the calculation of the Hamming distance is equivalent to maximizing a linear function. Okay, so you can see that. So you can extend it to the Rn rather than the hypercube. This is the original problem where it's still over the combinatorial set, subject to a linear constraint being at least beta. So you maximize beta. That's the same as maximizing the linear constraint. And the dual problem for this is the minimization of the constraints subject to the objective value being more than beta. So you can relate the opt1 to opt2. And now for this opt2 is where we use the integrality gap. Okay? So we're assuming that there exists a way to minimize this CSP by going to what are called pseudo distributions. Maybe I don't have time to go into these. And then from this SDP2, we're going back to the SDP1. This set F prime is never actually explicitly defined. It can be seen as the projection of this higher dimensional object, but we don't have to define it explicitly. And so if alpha is the integrality gap between these two problems, which is well studied in the computer science community, then you get that the value of Cn prime is the Rademacher averages of the set F where the number of constraints is enlarged by alpha. Okay, so this is just a simple calculation. Right? Any questions about this? So the way that alpha, this integrality gap, enters is through the number of constraints that are violated.
Just to get how you got around the problem that option problem is not solvable is because the algorithm that you had depended only on ability to evaluate phi rather than.
Right, exactly. So the whole point here, exactly, that the predictions are improper. I'm not trying to find a max cut and then output some prediction. I just need to evaluate the phi function. I just need that real number, right? And that real number can be evaluated using the approximation algorithms, but not directly, but in this dual problem, where it's the number of constraints being unsatisfied or satisfied.
Sasha, wait. On this slide, are you taking the assumption that f prime is an SDP relaxation of f kappa as an illustrative example of relaxation?
Yeah,
or are you
it's
saying that your theorem holds only when f prime is an SDP relaxation?
No, so this is just a way to relate. So this is just an example of how to use the integrality gap in the analysis to understand how the set f and f prime in terms of the width are related. Yeah. Okay, so now the question, do we have these algorithms that will give us that alpha, the integrality gap? And if one looks at for instance, the Guruswamy CNOP, it's a general result for quadratic integer programs, right? We're minimizing quadratic subject to linear constraints. And it shows that if you spend n to the r time, n is the size of the problem, then the integrality gap is the inverse of the roughly inverse of the eigenvalue of the Laplacian of the normalized Laplacian. One can also use metric labeling relaxation, so it doesn't have to be SDP. One can work with LP relaxations. And here we're looking at a slightly different problem where the constraints are penalizing rather than being hard constraints. An interesting feature of this is that you don't actually need the rounded solution, as I mentioned before. You just need the value. And so, in some sense, if in a week someone proves a tighter result for the integrality gap, well, we just plug it into the theoretical bound. The algorithm doesn't change, right? It's just like a general SDP relaxation. Okay, so let me skip the results. Let me just say that we implemented the algorithms without hoping that it will work, but it actually works very well, and it seems to outperform the Laplacian regularization or other methods that are really not tailored to online problems. They're tailored to a batch problem, right? So you can, of course, you can try different methods and hope that they work, but they probably have been developed for the offline problem where you have lots of data, and then you try to learn from these data. And here we're just going after exactly what we want, right? We're minimizing exactly the function that we want to minimize, the number of mistakes. So we're modeling solutions. If you think about the kind of philosophically, we're modeling the set of solutions rather than the process that generates the data. And this is the online learning philosophy. One can say that this is a pessimistic framework, but this function phi is exactly reflecting our knowledge about the world, right? We're not trying to do something for free. We're choosing this phi function to correspond to what we think is happening in the world. For instance, the labeling should be smooth with respect to the graph. Okay. And the predictions are improper, and this is key. So let me just sketch, give you a sense of how this can be extended. We've extended these results to side information at the nodes, general cost functions. You can work with an evolving network whose generative process you know or you can estimate. And I think the interesting results now are in partial information where you display the advertisement, but you don't know if the person didn't click, you don't know the value, or the kind of the observations are censored. So if you have side information at the nodes, the protocol is that you observe the side information for the person, you make a prediction, and then you observe the outcome. And typically in machine learning, people posit a class of functions, support vector machines, neural networks, whatever, that you hope are capturing the relationship between X and Y. And the question is how to merge these two sources of information, the graph-based information and the information in the covariates. And this is one way to do it. You can look at the projection of the function class onto the data, and that's a subset of the hypercube. Now, this might be large, and so you hope that the graph now narrows down the set. So the network constraints, when you intersect them with the constraints from the function class, are helping in making the set of labeling smaller, right? So now you would like to do as well as this set of labels. And we have experiments where you can tune a parameter, how much the algorithm relies on the information in the covariates and the information coming from the network. And as you tune that parameter, the algorithm either goes after this information or after the information within the network. So you can see that if the network has, for instance, the small cut, so you're just a few nodes within one community is enough to start filling in the other nodes, then these network constraints are kicking in. If somehow the covariates provide you a lot of information, males are buying this type of product and females are buying another type of product, then these constraints are kicking in. Okay, so a general setup is through what we call relaxations, and this idea is not new. So what we want is we want a strategy that depends on the covariates observed so far and the labels observed so far, such that for any outcome that will come, you make a prediction, you observe the outcome, the loss, this is a loss function that compares the prediction and the outcome, is bounded by the difference in the potential. Okay? So suppose that you can come up with such functions phi. If you can do that, then of course everything telescopes, and you get phi0 minus phi n, and this is the analog of the phi0 is data independent, that's the constant, right? That's how much you have to correct it. And the minus phi n is basically the Hamming distance, okay? So that's the analog for a general relaxation. So we'll say that phi is admissible if for any xt, when you take the minimum over possible predictions and the maximum over possible outcomes, the loss plus the potential is no more than the potential at the previous step. So this is kind of a standard thing in online learning. If we ensure that phi n is at least this comparator, this is the performance of the functions, the best performance of these experts in the class F that map side information into predictions, then the function is admissible, and then it can be used for prediction. And the whole question is how to come up with these potential functions. So what we have is kind of a toolkit for deriving these phi functions using techniques in probability theory. So symmetrization, sequential symmetrization, and so forth. So admissibility can be checked by martingale inequalities and sequential symmetrization. What's interesting is that the function phi, just like in this example, the set f, parameterizes the algorithm, right? Once you fix this f, or once you fix this phi, that gives you an algorithm, exponential weights, gradient descent, whatever. And so we have kind of a way to move in the space of algorithms, right? There's some kind of algebra of these relaxations where you can take two relaxations, combine them, and so it's nice that you have some kind of basis in which to move in terms of algorithms, right? The possibilities. When you have a partial information, the admissibility condition becomes like this. The phi is now evaluated at the information that you have so far. So you might not observe the actual outcomes, but you observe some partial information, and this becomes the admissibility condition. And so let me spend maybe 2 minutes on contextual multi-term bandit, which can be solved at least to some extent using the same machinery. So suppose I'm a host at a party, I have to serve drinks, and people come to me one by one, and I offer them a drink. And there are D drinks, D options that I have. And of course, the usual multi-term bandit says that, the classical multi-term bandit says that there is one drink that's best for all people. But of course, that's not the case, right? You have some, the drink type should depend on whether maybe the gender, maybe some other characteristics of the person. So I should make my decisions based on what I see about the person coming to me. And I'm okay assuming that the covariates are IID, so these people just come from some pool of people at the party. And but I don't want to make assumptions about the costs. So I observe the cost, whether the person liked the drink, but I don't want to make any stochastic assumptions about these costs. And we'll model this in terms of this individual sequence prediction setting where you make no assumptions on the costs. And what you would like is to have an average cost of your decisions to be compared to the best policy that what would have happened had you followed this policy that maps covariates to decisions of which drink to serve and then the cost of that drink. Of course, you don't observe the outcomes for the drinks that you haven't served, so this becomes a explore-exploit problem. And it's been a hard problem. So there is very slow progress on this problem, precisely because it's not clear what to do in this case. The space of algorithms somehow is not so clear, right? In the IID case, we know what to do. Basically, you need to estimate something. But in this individual sequence scenario, the contextual bandit has been a difficult problem. So long story short, we need to show that some phi function of information is admissible in the sense that I showed before. Let me not go into the details. And that leads to a simple Bistro algorithm that gets a bound for this contextual bandit problem. Suppose that now you want to take the network constraints into account, so you can intersect the values of the functions at the nodes with the constraints. For instance, you can model things like, I think there will be a part of the network somewhere where people will like this product. These could be a bunch of combinatorial structures within the graph, and you can easily put that as a constraint. Okay, so let me conclude. I think we have new avenues for the development of online methods. The simplest one being this phi function that arises from this Tom Kover result 50 years ago. There are some now well-established probabilistic empirical process techniques to help in developing these efficient algorithms. What I presented today is hopefully an example of a marriage of an approximation algorithms and online relaxations. So I'm hoping to get the computer science theory people interested in this set of problems. We have a knob for accuracy versus computation. And I guess the main thing here is that the predictions are improper, and that's what drives the computational efficiency. So there is a tutorial that we put up online with basically what I discussed today. There is a book draft that will take some years to complete, and maybe I put up some open problems. So I think it would be interesting to develop linear and sublinear methods for large-scale graphs. The problem that I described in the beginning, I think is very natural. It's a sequential decision problem, and we would like to be linear or sublinear in the size of the graph. And right now, we at least need to invert some matrix, and so we can't go more than 10,000 nodes, for instance. I think it's interesting to develop results for evolving graphs. where you don't know the evolution of the graph, but the graph changes as you go. I think it's interesting to explore which phi functions in terms of modeling are good in practice and lead to good predictions in practice. It would be interesting to get a complete story with partial information. I just sketched a brief result in that direction. That should be enough. Thank you.
Time for a couple quick questions.
So for contextual bandits, I mean, did you get the little of bandit, right? Or?
Yes. So we got 3/4. Then this was within a few months using very similar techniques improved by Vasilis and co-authors and Rob Shapir and co-authors to 2/3, and we're working on trying to get it to 1/2, which is the power 1/2, which is what it should be. We're not there yet, but.
The width related to like sort of the width that arises in like say packing covering problems, is there some connection between these two?
I don't know.
Okay, thanks Sasha again.